Hello, I'm Seema and welcome to part 21 of the chapter States of Matter. In the past few videos, I have been telling you about ideal gases. We discussed the gas laws and I told you that these laws are obeyed only by ideal gases. We did the ideal gas equation, which is PV is equal to nRT, and I told you ideal gases are those which obey the gas laws under all conditions of temperature and pressure. But an ideal gas is not a real gas, or in reality, gases do not behave ideally. Let me just explain this concept of ideal and real. Who would be an ideal student of chemistry to me? Someone who studies chemistry thoroughly, who spends maybe 90% of his day just studying chemistry and is ready to research further, go much beyond the book and just be involved only in chemistry and forget the rest of his life. But does that happen? In reality, you would get distracted. You might want to go for a picnic with your friends on a day. You might want to relax on a day and not study all the time. You would not like to spend 90% of your day just doing chemistry and the other 10% for all other activities. So, real life or a real student is very different from an ideal student. I'm not saying you have to be ideal. That's an extreme. It's the same with these molecules. These guys, we expect them to be ideal, but they are real. They are real guys, that is these molecules that form the gases, and these guys also cannot behave ideally. So the topic of this video is the behavior of real gases and deviation from ideal behavior. That is, they move away from that ideal behavior, and we're going to try and understand why do gases not behave ideally? Why do students not behave as the ideal students? Why do these guys not behave ideally? Because there are two faults in the kinetic molecular theory of gases. But before I come to those two faults, let me just see how did we know that gases do not behave ideally. According to Boyles Law, PV is constant. The product of pressure and volume is constant when temperature and number of moles are fixed. If PV is constant, then whatever, as we keep increasing the pressure, the volume should go on decreasing in such a way that the product of pressure and volume should remain the same. So if we plot a graph between PV and P, we should obtain a straight line. So that is what would be expected, and this straight line is that of an ideal gas. That is, if PV was always constant. But in reality, when we took these gases, we took hydrogen and helium, and we found they formed lines that were straight, but that did not coincide with the ideal gas. They showed positive deviation, a constant positive deviation. And then there were gases like carbon monoxide and methane. What did they do? They first showed a negative deviation, and then they would go up and have a curve that is positive. At somewhere they would cut the line, the ideal gas line, and then they would show a positive deviation, which means that real gases do not behave ideally. This is what was noticed. And another graph was plotted according to Boyles Law. If you plot a curve between pressure and volume, you would get a curve of this shape. We did get a curve of that shape, but when we assumed the gas to be ideal, we got the blue curve. But the real gas showed a little deviation from that curve. What happened with the real gas? If you see it in green, the real gas at high pressures, the real gas showed more volume than expected of an ideal gas. So when the pressure was high, the volume of a real gas was more than what you would expect if it was an ideal gas. So this is the curve. The blue curve is assuming that the gas is ideal, and it is a theoretically plotted curve, while the real gas is the experimental curve, which does not coincide with it at high pressures. But at low pressures, both of them seemed to be almost the same. So these two graphs, they pointed towards a fault in the kinetic molecular theory of gases. There were two assumptions in the kinetic molecular theory which were faulty. And what were these faulty postulates? The first one was that there is no force of attraction between molecules. Those guys have no attraction between them. You leave 2 students or leave 10 students out just in a classroom randomly, and there's no teacher, they are unsupervised, and they're just sitting there and they're just looking at the other 9. Do you think there would be no interaction between the children? Would they not be attracted? That guy seems good, he could be my friend. That one's nice, I could go and exchange some notes, he looks like the studious kind. So we find that imagining that the molecules do not have any kind of attraction or no force of attraction could be there would have been wrong. There has to be some kind of an attraction, right? And then there was the second postulate that was wrong, which said that volume of molecules is negligible. However small may be the volume of the molecules, however small an object is or a particle is, it does have volume is one thing. To assume that it is absolutely negligible is wrong. There has to be some volume that it occupies. But even if that volume that it occupies is extremely small, the actual volume that a substance occupies is always a little more than the volume it has. Like I just tell you, we just huddle 10 students together. And if we are huddling them together, I have 10 people all around me when they were the same classroom. Now those students were at a distance, they were attracted to me. Okay, this one's good, that one's good. But when they came too close, and they came so close, the room started, let's say the walls started moving in. Now the students are coming closer and closer and closer together. How do you feel? How do you feel when the students, when the molecules, those guys, they start coming close? You feel that now, hey, I need some room space. Would you please move a little? I need some room for my arms. Or I need some room to breathe. Oh, come on, give me my space. So as soon as the molecules, they start coming a little too close, instead of that attraction may have brought it closer. But after a certain distance, you need your own space. That is, repulsion comes into play. Beyond a certain distance, even if there is space between the 2 molecules, these molecules cannot really be huddled together like that. They can't be crushed together. They can't be smashed together. So there has to be a distance between the molecules. I just took an example here. These are a few pens, right? They are randomly kept. And they are occupying a lot of volume because they've been randomly, now the shapes don't match, the orientation is not right, so they are occupying a lot of space. But if I had these pens like I have them in this box, which are kept very nicely together in a certain form, like do you see an arrangement? This arrangement is such that there is space between, yet you can see there is space between the pens. So this space, whatever, even if they are huddled together, the actual volume of these pens, the tops of these pens is less than the volume that they are now occupying. Because you do see spaces in between them. So the kinetic molecular theory does not account for this space. You cannot bring them closer than this, come what may. They cannot occupy space less than this. So this, and while their actual volume is less, but the volume that they occupy is more than what their true volume is. This was not taken into consideration when the kinetic molecular theory of gases was given. So this postulate that volume of molecules is negligible. It may be negligible on its own, but the volume that it is occupying, the arm space, the room it needs, the little distance due to repulsion that it has, was not taken into account. So what was the result of these 2 faulty postulates? It was these 2 faulty postulates which were the reason why gases did not behave ideally. So let us take them one by one. The first postulate that was wrong was that no force of attraction exists between the molecules. if there was no force of attraction between molecules, can you imagine, could we have liquefied gases? Could we have gases turn into liquids and they stay like that because there is attraction between molecules? So when you bring the molecules closer, they get liquefied under pressure, and at low temperatures, gases do get liquefied, which would not be possible if there was no force of attraction, right? But they cannot be compressed once they turn into liquids, although there is space between the molecules of a liquid. That is because of the faulty second postulate, that the volume is negligible. The volume is a little, the actual volume that they occupy is a little more. So we say that instead of, besides the forces of attraction, there definitely are forces of repulsion. Now what happens as a result of this? Imagine you are running in a race, and when you're running fast, there's someone, or rather me, I'm a little, I like to do such things. So I just come behind you and I'm invisible, and because I don't like running, but I just come behind you and I hold you by your t-shirt. And I hold you by your t-shirt and you're running to the finish line. And when I hold you by your t-shirt and I pull you back a little, would you be able to touch the finish line with the same force as you would have if I would not have interfered, if I would not have attracted you towards the back from behind? So what happens? Have you seen that belt in the gym that they use? They put a belt around you, the trainer, and then you're expected to run. You're expected to run. You're running and running with the belt around your waist, which is pulling you behind, and you're reaching nowhere. But you're just running. So with these guys, it's not so bad. What happens? They are running in a race, they are moving towards the walls of the container, and they're just headed towards it. But the other molecules, they attract them from behind, and therefore the impact with which it would have hit the wall is a little less than what it would be if there was no force of attraction. In other words, the actual pressure of the gas that we observe is less than what it would be if it was an ideal gas, because if it was an ideal gas, there would be no attraction, there would be no other guy back there pulling it behind and not letting it touch the finish line. So we say that the pressure of an ideal gas is actually the pressure of the real gas that is observed plus that force of attraction with which the other molecules were pulling it inwards. That amount of force the impact will have, the pressure with which it hits, is less by how much? By this much. And this is the force of attraction, the magnitude of the force of attraction. So this equation was given where a correction term was put in. They said that the pressure of an ideal gas would be equal to the pressure of the real gas, the one that is observed, plus that amount of attraction that it was experiencing by the other molecules, which did not let it impact the wall with this pressure. Rather, the pressure was slightly less. So this pressure with which it is actually impacting plus the force of attraction together would make P ideal. Right? So this was written as a correction. This correction term was added to the pressure of the ideal gas. And why was this correction term added? Because now we wanted to change the ideal gas equation into a real gas equation. In order to change the ideal gas equation into a gas equation which would be applicable to real gases, we had to bring about this correction term and take into account the forces of attraction that are there in a molecule. So the equation now became P ideal is equal to P real, which is the observed pressure, plus An square upon V square, where A is a constant, N is the number of moles, and V is the volume of the gas. So this is known as the correction term, which gives you the magnitude of attractive forces. Then the second was the volume of molecules is negligible. And I told you here is where the repulsive forces come into play. That the volume, although actual volume may be negligible. So for an ideal gas, the volume may be negligible. But the repulsive forces are forcing the molecules to occupy a little more space than they would actually do. Why are they occupying a little more space? Because come what may, they cannot be smashed more. They cannot come closer than this. So whatever their volume is, the actual volume cannot be absolutely negligible. They are occupying some space which is a little more than their actual space, and now the volume available for molecules to move around is decreased by that volume. I just explained. If we have, let us say, this was a space, a room, and you have molecules which are negligible. So now these molecules have all the space to move around in the room because the volume they occupy was negligible. So we will not even think that this molecule which was present at this point is not available for the molecules to move around, because we are assuming that this volume that it is occupying is negligible. But for a real gas we find it's not so. Now even if there were 10 molecules and they occupy 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Let us assume they occupy this much volume like we did with the pens and where the repulsive forces were coming into play. Now the actual volume available to the gas molecules is only this, and this volume that they are occupying is not available for their movement. So the actual volume available for movement is the total volume minus the volume that was occupied by the molecules. So there had to be a correction term in the volume also. And this correction term, the volume available for the movement of the molecules, was written as V, that you would expect the volume, the total volume, minus the actual volume occupied by the molecules, which is known as NB. Where again, B is a constant and N is the number of moles, because we know the number of molecules will decide how much volume would they occupy. And again, these would depend on the nature of the gas that you've taken, right? What is the gas that you've taken? That will decide these values. So now these correction terms we observed for the ideal gas equation, we needed to add correction terms to both the pressure and volume. So let us now come to the ideal gas equation. The ideal gas equation is PV is equal to nRT. So if we now put the value of P as P real plus this, that is along with the correction term, and if we put volume as this with the correction term, we get an equation that P real plus AN square upon V square into the volume with the correction term V minus NV. Now this should be equal to nRT. This is the real gas equation, and it is commonly known as the van der Waals equation. And these two constants in this equation, that is A and B, these constants are known as the van der Waals constants. They are known as van der Waals constants. So now we find that real gases do not follow the gas laws under all temperature and pressure conditions. They cannot do so, and real gases deviate from ideal behavior. We know the reasons why they do, the two faulty postulates, and how we needed to make correction in the pressure and volume terms, and how we arrived at this real gas equation or the van der Waals equation. Now I'll tell you just one more thing before I finish this video. Now these A and B were called van der Waals constants. So we know for an ideal gas, PV is equal to nRT. So the ratio of PV upon nRT should be equal to 1 for an ideal gas. Because if a gas is following this equation, then PV upon nRT should be 1. This ratio of PV upon nRT is known as the compressibility factor. And it is represented by the symbol Z, the capital Z. So compressibility factor, which is equal to PV upon nRT, for an ideal gas, it should be equal to 1. But we know that gases are not ideal. And if they are not ideal, compressibility factor for real gases will not be equal to 1. And when we plot a graph between compressibility factor and pressure, compressibility factor for an ideal gas should always be 1. Just as I said, the product of pressure and volume for an ideal gas should always be constant. It may not be 1, but it is always constant. But compressibility factor should always be 1. So if we plot a graph between compressibility factor and pressure, we should get a straight line with the value 1. 1 of the compressibility factor for all gases, or rather for ideal gases. And we find for real gases, again, the curve we obtain does not coincide with the ideal gas curve. The reason for this and more about compressibility factor I'll tell you in the next video. If you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.